We just looked at end behavior of polynomials, but we specifically said in that section that we didn't know what the middle of the graph looked like. So now we need to work on that. Part of that is finding the zeros of the polynomial. So let's define that and then talk about how that helps us with the graph. X equals c is a zero of f of x if f of c is equal to 0. If x equals c is a zero of f of x, then that means our input is c, our output is 0, so we get this ordered pair, right? C0. Well, C0 is going to be an x-intercept of the graph of f of x. So the zeros of the function correspond to x-intercepts of the graph of the function. Let's take a look at this example. Notice we are looking for x values that we would plug in that would give us an output of 0, or where is the function equal to 0? Well, this one's nice because it's already in factored form, so we set the factors equal to 0, just like we did back in Unit 1 with the quadratics. We don't need to worry about the 3 because 3 is never equal to 0. So the only way this can equal 0 is if x is -2, x is 4, or x is 3. Those are our zeros of h of x here. This one we have to work a little bit harder because it's not already in factored form. We are still trying to accomplish the same goal, though, of finding out where g of x is equal to 0. What x values make that true? I think the easiest way to do this would be to factor out the GCF, which would be -2x squared. X squared minus 4x plus 4. And that gives us -2x squared times x minus 2 quantity squared. We want to know where that is equal to 0. That happens when the factors equal 0. Dividing both sides by 2 gives x squared equals 0, which tells us x equals plus or minus 0, which is kind of silly, but x equals 0. Here, if we square root both sides of this, we get x minus 2 is 0. And x equals 2. So those are our zeros here. The only way x minus 2 quantity squared can equal 0 is if x minus 2 is equal to 0. So that's another way to think about that. Notice on the first example that we see on our screen here that if we multiplied that out, we would get 3x cubed plus some other business of smaller degree, right? So this is a polynomial of degree 3. We got 3 zeros for that. This function, this g of x, the second example on your screen, is a polynomial of degree 4. It's already multiplied out, so we can see what that degree is pretty easily. We would kind of expect to get 4 zeros, but we only got 2. Oh, excuse me. So we need to think about why and what's going on there. That's where the multiplicity of a 0 comes into play a little bit. The 0 x equals c of f of x has multiplicity k if x minus c occurs k times in the factorization of f of x. The zeros come from x minus that number being in the factorization, right? So let me show you what I mean here. Let's go back up to this one. X plus 2, that's really x minus -2, right? And then notice the -2 was a 0. X minus 4, right? X minus 3 gave us this 0 of 3. So anything that has a linear factor of x minus that number is going to be a 0 of our polynomial. So that x minus c is going to occur when x equals c is a 0. What we need to know, though, is how many times does the x minus c actually happen? This g of x here factored into negative 2x squared times x minus 2 squared. Notice that this x squared could be thought of as x minus 0 squared, and then we have x minus 2 squared. That's kind of a weird way to write that, and we wouldn't normally, but I want you to kind of think about that x equals 0 coming from that factor right there. And so it's going to have multiplicity equal to 2 because I have that square there, right? It's like having x minus 0 times x minus 0. Same thing with x equals 2. That's going to have multiplicity equal to 2 as well because of the square on that. The example above that, each of these zeros has multiplicity of 1 because the factor only occurs one time in that factored form. Here's another example. For p of t, we have zeros. Remember, we set this equal to 0 and solve. And we get, remember 2 can't equal 0, but t plus 1 can equal 0. T minus 1/2 can equal 0, and t plus 4 could equal 0. This one gives us t equals negative 1, t equals 1/2, t equals negative 4. And then multiplicity of each of these for t equals negative 1. The multiplicity will be 2 because that's squared. It's like having t plus 1 times t plus 1. T equals 1/2 is going to have multiplicity 2 because of that cube. T equals negative 4 will have multiplicity equal to 1 because that t plus 4 only shows up one time. Okay. Those are our zeros, and that's the multiplicity. You should always be asking yourself why. Why do we care about the multiplicity? What does that tell us? Because remember, we said that our goal is to pull all these details together to help us graph these functions, these polynomial functions. So far, we talked about the end behavior, and then we said, okay, well, we know nothing about the middle. So let's find some information about the middle. Well, now we know that these zeros correspond to x-intercepts of the polynomial, but there's 2 ways that you can have an x-intercept. You can have an x-intercept by the function crossing through like this or like this, or you can have an x-intercept by the function coming up, hitting the x-axis and turning around and going back down, or vice versa, coming down, hitting it and turning around and going back down. So you can have, this is the idea of it crossing, and this is the touching situation. The x-intercept, or the graph only touches the axis and then turns around. We have these 2 scenarios based on the multiplicity of the zero. So that's why we care about the multiplicity of the zeros. If the multiplicity of a 0 is even, then it just touches. And I always think of this like the standard parabola. Y equals x squared has zeros. 0 of x equals 0, but it has multiplicity 2 because of the square. So that's what always helps me with that, because I know that's the standard parabola. It comes down, it hits the axis, and then it turns around and goes back up from the vertex. If x equals 3 is a zero of odd multiplicity, then it crosses. So you're going to have one of these two pictures in this top picture here. Either comes down and crosses or increases and crosses. That's with odd multiplicity. In that case, you can think of like y equals x, that line that goes like this, right? It has multiplicity of 1 on x equals 0, multiplicity of 1. So it crosses through the axis there. That would be true for any line. Okay, let's take a look at this function. F of x equals x to the fourth minus 4x squared plus 4. So let's find the zeros first. We find the zeros by setting the function equal to 0. This is, if you remember back from Unit 1, this is an equation of the quadratic type. And if it's going to factor, it's going to factor into x squared and x squared to give the x to the fourth, and only give x squared in the middle, not give an x cubed term. All right, if I have -2 and -2 here, I think that's going to do it, because my first two, when I distribute the first two terms here, I get the x to the fourth. When I do the last, the L in FOIL, that distributing, I get the 4. And the OI part of FOIL, the outside and the inside, gives me that -4x. Okay. Set those factors equal to 0. The easiest way to solve this is to use our square root property. Square root both sides, and you get x equals plus or minus the square root of 2. But I get the same thing here. So x equals plus or minus root 2 is the same there. Because I get that twice, the zeros, let's do this, zeros, multiplicity, and then behavior. Let's just organize it into a table here. Okay, my zeros, I get positive square root of 2. What's going on here? There we go. Positive square root of 2 and negative root 2. The multiplicity of both of those is 2. If I tried to write this in factored form, I could, let me come down here. I could rewrite this equation as 0 equals x minus root 2, x plus root 2, and those would show up twice. I know we don't usually factor when we have irrational numbers like the square root of 2, but you can, because we don't typically. The behavior is that it touches and turns around, right? Because these have even multiplicity. Both of these are going to have that picture. I did pull this up. Let's look at this on the graphing calculator. X to the fourth minus 4x squared plus 4. I did put this in the calculator. Let me turn off that second one there, so we're not looking at it. If we take a look and graph this here, you can kind of see what I'm talking about. Let me show you how to find zeros in the calculator. It's in the same place that we find a minimum or a maximum of a function, which was in this calc menu. So second, trace. We've used the minimum and the maximum before. Now let's do this 0, number 2 there. 0, and it's going to ask the same things, a left bound and a right bound. So if I want to find this leftmost one, you have to find these each separately. Remember, a 0 is an x-intercept, so I want to go to the left of that, hit enter, go to the right of just that one that I'm looking for. Don't go all the way to the right. And then the guess, get it as close as you can there. Hit enter. And it gives us x equals negative 1.414 and so on. Well, if you throw the square root of 2 in your calculator, you're going to get approximately 1.4. So that is where that's coming from. The same thing would happen if you found the 0. Remember, I'm just going to go through it one more time. Second, calc. Oops. Oh, hold on. I think I got to get out of here. Yep. Second, calc, 0, number 2. And now I want to find the other one. So I'm going to go over here. I want to be to the right of it, but close enough. I'm sorry, to the left of it, but close enough that it doesn't take forever to do the calculations to find it. Then to the right of it, and then a guess. The closer you guess, the faster the calculation will happen. And there it gives you the 0 positive square root of 2, the approximation of that. I will want exact answers, so this only sort of helps because that you're not going to recognize that as the square root of 2. Okay. Notice also that those in that graph, it just touched and turned. It came down, touched, and turned around and went back up on both of those. All right, let's look at one more. First, we have to find the zeros. So we set the function equal to 0 because that's what it's asking us to do. It's not just a default. We always just set the function equal to 0. We do that because it's asking us to find the zeros. Well, we need to be able to factor this. When I see 4 terms, first thing that pops into my head is factoring by grouping. I don't like that negative there, so if I have a negative there and I add parentheses, I have to change that second sign so that if I distributed that negative, I would get back to what I started with. Factoring by grouping says you take the GCF out of the first term, then we take the GCF out of the second term. Fortunately, these match, so they become our new GCF and get factored out. You factor it out of the first one, you get x squared minus, or you get x squared. When you factor x minus 3 out of the second one, you get x squared minus 9. X minus 3 times x minus 3 times x plus 3. More commonly, we might see this written as x minus 3 quantity squared times x plus 3. Remember, we're set equal to 0 here, so we set each factor equal to 0. The square on there doesn't change the solution of that, so I always kind of ignore that exponent for finding the zeros at least. Organize here, 0, let's do the multiplicity and then the behavior because that's what it's asking for. We found 3 and negative 3 as a 0. X equals 3 has multiplicity 2 because it came from this. And that has exponent of 2 on it. X equals negative 3 has multiplicity of 1 because it came from this second factor there, and that only shows up one time. If the multiplicity is even, the graph just touches the axis at x equals 3. At x equals negative 1, at x equals negative 3, the multiplicity is 1, which is odd, so it's going to cross. Let's take a look at the graph of this function and see if it does behave the same way that we just found. See if it behaves what we found. I'm going to turn this one off and turn this one on. You do that by just hitting enter on the equal sign. go ahead and graph here. Might need to zoom out a little bit so that I can see a better picture. So I go to zoom and number 3 and then hit enter. So that kind of gives you an idea, better idea here. I am going to zoom back in, but I wanted you to see this is a cubic function so that end behavior we could figure out goes up to the right and down to the left. Zoom back in a little bit here so we can really look at those zeros, which is what we're focused on. We have a 0 at -3 and it crosses there. We have a 0 here at 3 and it just touches. Let's make sure that's what we got. At -3 it crossed, at +3 it touched. That's how you study zeros in of polynomials and what information they give you about the graph of the polynomial. I'm going to skip this space here on finding zeros on the calculator because we already did that. So if you need to review on that or more practice on that, just pause this video and go back, rewind to that point of the video. I'm going to stop here. The zeros of a polynomial are a big enough topic on their own that I think that it warrants taking some extra time. So pause here, reflect on this, work on some homework, and make sure you understand what's going on here.